So to get from the data table representation of this relationship and the graphical representation of this relationship, to get from those two things to an equation that captures this relationship, what we really need to do is we need to ask ourselves, what is it that makes a straight line straight? This is not an obvious question, or one that we're asked to wrestle with very often, because usually it's sort of like that classic story about pornography in the Supreme Court. I don't know how to define it, but I know it when I see it. Right? That's usually what we say about lines. Right? I know it's a straight line because it looks straight, but we need to do better than that if our goal is to get to a formula for this relationship. So here's an idea. There's a few points on this line that I sort of deliberately chose so that they're nice and evenly spaced. Right? These four that are kind of here in the middle, they look like they're evenly spaced apart from one another. So let's find those four inside my data table, and let's throw out the other two, just so we can focus on the ones that we might be able to do something with. So here's the graph with just those four nicely evenly spaced data points in it. So let's take a look into the data table, and maybe just single out two of these points. Maybe just this one and this one. These are the first two that we placed, 75, 500, 85, 400. They're the first two data points in the rows of this table. If I want to go from one of these points to the next, let's say we go from the first data point that we put onto the graph, 75, 500, and I go to 85, 400, and I ask, what's different about those two data points? The x and the y coordinates are different, right, for both of them, but how are they different? How would I describe the process, maybe in marketing lingo, of going from that first test market to the second test market? What have I done to the price of iPhones? Yeah, the price went down, and how much did it go down? Right. So we dropped the price by $100. If we look into the data table, here are those two data points, and there is that $100 difference. How do we know it was $100, by the way? Where'd that 100 number come from? Probably you looked at that and got it by subtracting 400 minus 500, right? So that number, 100, came from a subtraction problem, right? Take this y-coordinate and subtract that y-coordinate, and that gives me negative 100, which means that the difference between those two markets is that the second market has a price point that's $100 lower. Right? So negative 100 is what we get by subtracting those y's. So that's what happens with the prices. But what happens with the quantities? So what would you describe as happening to the number of iPhones that are being sold here as they go from the first market to the second? Yeah, here the quantity is increasing, again, because this is a decreasing relationship, a decreasing function. When one of these quantities goes down, the other one goes up. So the quantity went up by how much? By 10. 10 million iPhones, right? So that 10, again, is a number that we could have gotten. I'm going to write plus 10 over here. We could have gotten that number by subtracting 85 minus 75. Right? That's where that number 10 comes from. So what we'd like in order to capture this relationship is we'd like to understand how those two changes are related one to another. Right? Why is it that every time I drop the price by $100, I sell 10 more millions of iPhones? Right? And if that pattern were to continue, does it also explain why these other points are placed where they are? So let's investigate that for a second. So let me clear out what we have here and just put back in here again that here the difference is 10 additional millions of units of iPhones combined with a $100 drop in the price. And that relates these two data points together. What about the other pairs of data points that are on this list? Does that same relationship still hold if I compare, let's say, the middle, let's say the point right here and the point right there, which in the data table are the second row and the third row? Does that same relationship hold? It does. Right? That same $100 decrease in the price is combined with that same 10 million unit increase in the quantity that's sold. Right? For not just the two data points on the end, but also the two data points in the middle. And also the two data points on the left side. Right? The first and the second data point right here. That same relationship remains true. And that's the pattern that's starting to emerge, right? That the relationship between the differences in the y values and the differences in the x values is the same from point to point to point. And that is what ends up making this graph into a straight line. But then the question comes in, well, what if I'm not choosing 2 points that are next to each other? What if I choose instead, let's say I choose these 2 points. So this would now be the first row of the table and the third row of the table. If we do that same process, let's figure out what gets produced there. So if I go from this market down to that market, how many fewer, sorry, what am I doing to the price of iPhones going from there to there? What's happening to the price? Decreasing by 200. So now we're looking at not a $100 price drop as we were before, but now we're looking at a $200 price drop. And then what's happening to the quantity that's being sold? Increasing by 20. So now we have a different combination of change in price, $200 price drop, and a change in quantity. Here this would be a $20 million unit increase in the quantity. And that same $200 price drop, 20 million sales increase, that same increase also happens to be the same relationship between the first and the third points in this table as well. So that gives us another mark of consistency. But the problem that we're faced with is how do we square both of the examples of change that we just looked at? So what I'm kind of asking, what is the same? What remains the same when we compare, when comparing the first set of changes, which was negative 100 and positive 10. In what way do those two numbers have the same relationship to our second pair of changes, which were minus 200 and plus 20? What's the same about those two comparisons? It's like an analogy on the old SAT exam. Negative 100 is linked to the change plus 10 in the same way that negative 200 is linked to the change plus 20. So what's the same about those two comparisons? How can I describe, maybe, how to turn one of these numbers into the other that works just as well for the first pair as it does for the second pair? Does anybody see what the relationship between the red numbers and the blue numbers is that's the same for both of these pairings? So we can look at it two ways. And again, this gets at the different ways of representing the same information using a graph, using a table, and using arithmetic. So let's look first at the graph. On the one hand, in the graph, I've got one triangle. I'm going to draw it like this. And in this triangle, two of the sides of this triangle are respectively negative 100 and positive 10. Suspend disbelief a little bit because usually distances are not negative, but we'll just suspend that for the moment. And in another one of these triangles, maybe I'll make it this one here. Another one of these triangles, instead of plus 10, we're going to have plus 20. Instead of minus 100, we're going to have minus 200. And the way that I think math majors tend to like to conceptualize this is we can look at these two triangles and say, oh, these two triangles have all the same angles in them, right? The green lines are parallel to one another. All the red lines are vertical. All the blue lines are horizontal. So all the angles are the same in both of these triangles. That means that these two triangles are similar triangles, and we know something about similar triangles, namely that their sides stand in the same proportion to one another, and we can use that to kind of pull out the arithmetic that we need for this. If you don't like geometry, I don't think that's a way that lands very well. So let's back that up a bit. And let me just ask you, what relationship exists between the number 10 and the number negative 100? How can I think about how to relate those two numbers together? How to turn one of them into the other, for example? Either by adding something, or by subtracting something, or multiplying something, or dividing something. How can I turn a 10 into a negative 100? By multiplying it by negative 10. So let's take that for a second and run with it, right? That one way of looking at this is that if I multiply the number on the right by negative 10, I end up getting the number on the left. Well, that works for the first pair, but we also notice that it works for the second pair. And I agree with that, right? That seems to be the nature of the consistent relationship between these two changes. That whatever the difference is in my x values, if I multiply that difference by negative 10, I get the corresponding difference in the y values. And a mathematician would say that's the constant of proportionality that relates the sides of these similar triangles. But that's overhead. We don't care about that. If we can note that this is the consistent relationship that we're looking for, then what it does is it elevates this number negative 10 to a special status. This number negative 10 tells us, in all cases, that if I divide the differences in my y values, which sometimes we represent by y2 minus y1, so a difference in two y values of 2 points on my graph. If I divide that difference by the corresponding difference in the x values, that ratio, this quotient, is always equal to negative 10. Right? So in one of these cases, the difference in the y's was negative 100, and the difference in the x's was positive 10. That quotient was negative 10. In the other case, the difference in the y's was negative 200. The difference in the x's was positive 20. We divide those, and we also get negative 10. And so then this relationship must be true not just for the data points that we see, but also for the data points that we don't yet see. For all cases, everywhere on this data table, even for the data points we don't have, everywhere on the line, even the points that we haven't marked with points on that line, this must always be true. And what do we call this ratio? Remember from your previous algebra experiences what this quotient here gets called? It gets called the slope of this linear relationship. And so the reason slope is so important, not just important for us in this course, but it is the most important concept in all of, I would say, first semester calculus. So it's not just valuable for now, it's valuable for later too. It's important because it tells us something so profound about the relationship between x's and y's in one of these relationships. And for historical reasons, we often denote it with the letter m. And what a lot of people remember about m is that m can be constructed using this process of subtracting y values, subtracting x values, and then dividing the former by the latter. And any 2 points on this line that I choose, if I do that process, I'm going to always end up with the same answer for my slope. And so negative 10 tells us a lot about this relationship. In particular, and I'm going to close with this, we can interpret that negative 10 in the following way, by first of all turning it back into a fraction, negative 10 over 1. Right? That's how we can always turn a whole number into a fraction. And then reinterpreting what this means in terms of iPhones. Because my numerator here, my y's, are prices. And so negative 10 means I drop the price by $10. And my denominator are the x's. Those are the quantities of iPhones that I would sell. And so there I would interpret this mean 1 million more sales. And so that's the practical import of that number negative 10. It tells me that in this marketing relationship, in this marketing data that we're looking at, the number negative 10 means that I will sell 1 million more iPhones for every $10 that I drop the price. And that's the interpretation. That's why the slope is so important to this relationship. It turns out it's only one part of the puzzle for finding a formula, but it's the most important part of the puzzle. And in a lot of these problems, it's the first thing that you set out to find for any linear relationship is finding its slope.